So let's wrap up this section on solving equations with fractions or decimal coefficients. So similar problems to last time, we'll use our addition and multiplication properties of equality to solve the equation, but the added complexity here is that we end up with fractions or decimals in the initial equation. So let's look at our first example together. Here is the step-by-step for how to actually solve this equation. It says that we need to find the least common denominator of all the fractions and decimals. Now, it's actually not necessary that we do this. We can solve this equation as if it were written in the following format, as if we had some whole number values here. Now, in a class where you don't have a calculator, it's very helpful to use the LCD method to actually eliminate the complexity here. So this is a similar structure to what we want to achieve. However, it's all the wrong numbers. So the idea behind using the LCD is that you find the least common multiple of all the denominator values, otherwise known as the LCD. And the LCD is what we use to multiply to create not just a simpler statement, but an equivalent equation. So what is the multiplying value that I can use that helps me in two ways: to one, eliminate all the fractions, and two, to create an equivalent statement. Again, it's based on what the denominator values are. So 12, 6, and 4. Well, the least common multiple between those values happens to be 12. And so I can use this as my multiplying value. So by multiplying the left and right hand side of this equation by 12, let's see what occurs. When I multiply 12 by 1/12, well, my numerator and denominator values cancel. I'm left with just x. Multiplying 12 times my second value here, 5/6, I get 12 divided by 6 is 2. 2 multiplied by my numerator value 5 gets me to 10. And on the right hand side, I can do something similar. 12 divided by 4 is 3. 3 times 3 is 9. Now, which equation, the original or x plus 10 equals 9, would you prefer to solve? The x plus 10 equals 9 is a single step to get to our solution. By subtraction, I get x is equal to -1. So we get to a conclusion fairly quickly here once we change the look of our problem. But the complexity comes in these problems from being able to determine what the LCD is and multiplying that to create an equivalent expression, and then using our general strategy for solving linear equations to finish off the problem. So let's look at some more examples. Let's start with the top example here. I have x over 4 plus 1/2 is equal to 5/8. So again, I want to determine what is the value that I can use to help me get rid of all of these fractions. And again, that comes from identifying the LCM between all my denominator values. So between 4, 2, and 8, the LCD, or LCM, however you want to think about it, would be, again, just one of those values, 8, because if I multiply everything by 8, by definition, they'll all be divisible. So let's look at how this occurs again. I want to multiply through distribution. I get 8 times x over 4. And I can think of x over 4 similarly to something like we saw earlier, 1/4 times x. So my multiplication here, I get 8 times 1/4, or 8 divided by 4 is 2. Multiplying by x gives me 2x. Another distribution here, I get 8 times 1/2, or 8 divided by 2 is going to give me positive 4. And on the other side here, we've got to also multiply by 8, and our terms here in the denominator will cancel with the whole number value 8, and we're left with 2x plus 4 is equal to 5. So now we've got a nice linear equation to work with. We introduce the operation of subtraction to move our constant terms to the same side. So 2x plus 4 minus 4, these terms will cancel, and I'm left with just 2x. And on the right, I got 5 minus 4 is 1. Now we introduce the operation of division. Again, we want to isolate our variable of interest and get a coefficient of 1. By division, we get 2 divided by 2 is 1 times x is x. And we end up with our solution, 1/2. So x equals 1/2 is the solution to our original statement. So let's look at a couple examples that look slightly different. You may think to yourself, in each of these two examples, my best course of action is to actually do the distribution right off the bat, but that's not necessarily the case. So in fact, let's look at this bottom example here. I have these fractions that are complicating the situation. Again, if I were to do the distribution here, I end up with more fractions than the original. And so again, we want to find some way to get rid of them. In this case, it's again multiplying by the LCD factor. So looking at my two denominator values, I have 5 and 4. What is the LCD that I need to use? Well, I can say in this case that it would be 20. 20 is the least common multiple between 5 and 4. So by multiplication, again, I can say that this will help me reduce all of my fractions. Now, it does not actually eliminate the need for distribution, but it does simplify our problem somewhat. So through multiplication here, I get 20 times 5 is 4, or excuse me, 20 divided by 5 is 4, multiplied by 1, my numerator, just gives me 4, but I'm still ultimately multiplying by this binomial here, x plus 3. On the other side, I have 1/4 times 20 is 5, and again, my binomial, x minus 7. Through distribution here, I get 4 times x is 4x. 4 times 3 gives me positive 12. And on the other side, I get 5 times x is 5x. And 5 times negative 7 will give me negative 35. So here we have a choice to make. Again, we want to isolate our variables to one side and constants to the other, ignoring whether or not they have some desired coefficient. In this case, I'm going to move, for instance, my variable terms to the left-hand side here by introducing subtraction of 5x. And I get here negative 35 is equal to negative 1x plus 12. Now by subtraction, I get rid of my constant term from one side. End up with a statement negative 1x, and I'll just write it as negative x, is equal to negative 35 minus 12. Being both negative, I'm going to ultimately end up with a negative answer here, adding those two together. So I actually get negative 47. Now at this stage, I'll sort of bring it over here to make some more room. I got negative 1 as my coefficient on the x term, but I need it to be positive 1. So I can think of this in a couple different ways. I can introduce the operation of multiplication by negative 1 or even division by negative 1. Either operation gets me the same result. Negative 1x, if I can think of it that way, divided by negative 1 results in positive value x. And on the other side, I get negative divided by negative is positive, and 47 would be the whole number value that I achieve. So there is my solution in this example. So let's look at one more example here where we have these decimal values for our coefficients. Now, for instance, when I have a calculator, this is not too bad, but I want to consider how I might approach this in a similar way to the last examples. Fractions and decimals are sort of two sides of the same token. And so if I consider the values that I have here, 0.1, 0.05, and 2.15, how might I consider these in terms of some decimal to fraction change? So something like 0.1 or 0.10 in this case could be thought of as 10 out of 100 for the fraction version. Well, same for here. We could say this is 5 out of 100. And the last one would be 215 out of 100. So constructing a fraction equivalent here can give me an idea of actually how I'm going to approach this problem. So consider if I were still trying to create an equivalent equation that didn't have this fraction nonsense, what would be the multiplying value that I could use? Well, if you'll notice, all three of these examples have the exact same denominator value. And if our LCM or LCD is based on that denominator value, then it's got to be 100. So multiplying all of these times 100 would yield a much simpler example. So let's do that. If I multiply my entire left side here by 100, 100 times 0.1 would give me 10x. 100 times 0.05, which is then multiplied by the binomial, but we'll leave that be for now. I get simply 5. And on the right-hand side, I end up with, when I multiply by 100, just 215, like this. So now we've eliminated the fractions. We can approach this using our general strategy. So by distribution, on the left-hand side here, I get 5 times x is 5x, and 5 times negative 5 is negative 25. So we have now two terms on the left-hand side that can be combined. 10x and 5x is going to give me 15x minus 25 here. So now I want to move constant terms to the same sides. By addition, I get now 15x is equal to 240. Right? So our final task here is, of course, to divide. And so we get 240 divided by 15 is equal to 16. So by division, and I've run out of room so I won't show it, we get x equals 16 for our conclusion. So that is one other way to interpret these decimal value coefficients, especially in cases where you may not have access to a nice fancy calculator. So that's going to be it for this section. Next time we'll talk about a problem solving strategy in section 2.2 and look at some more formulaic examples in 2.3 where we end up trying to solve equations that just have letter values, no numbers typically. All right, see you next time.